linear regression, we thought, okay, fine, let's now think of doing classification, right? And then we looked at some examples where we might be interested in doing classification, like classifying the email as spam versus ham or non-spam. And then we did say that for that thing, in order to make that easier, we would relabel our data. So what do we mean by relabel? So relabel means that we have to come up with this notion, like when you have spam versus a ham, meaning non-spam, we need to determine like which is going to be our positive class. So what do you mean by positive class, right? As an example, and what is a positive class here? Which one would you consider as positive? Okay, let's see. When we have to do a binary classification, right? Let's confine ourselves to the binary. We'll get into multi-class classification today only. But yeah, let's get it right for the binary case. Like, which label should we consider as positive? Do we have a good understanding about that? I think that one class, class A versus B, one of those should be treated. See, having COVID, if you think morally, right? If you think morally, or if you're not in data science community, right? And if you think about a moral point of view, right? So somebody having COVID positive is bad, right? So we'll feel bad about the person who has the COVID positive test. So morally, that is bad, right? Similarly, if we have a transaction which is fraud, then morally that is bad. Morally, we'll consider that this is a negative thing that has happened. Somebody did a transaction which was fraud. Okay, and similarly, we'll feel bad for the person who got tested positive. But our task that we have to, the model that we have to build is about identifying this event, COVID positivity, right? And similarly, finding out the fraud, that is there a fraud or not, right? So whatever we are undertaking as our task happens to be the positive class, right? It has nothing to do with the morality of that label. All right, so fraud, yeah, morally this is negative. We should not have negative transactions. But if we are building a model which has to identify fraud from the data, then the instances of fraud in my data are going to be my positive sample, a positive label, I should say, positive label. Does it help? Right? So spam would be positive, right? For cancer versus healthy, if you need to identify whether a person has cancer or not, then the cancer will happen to be, we'll consider that as the positive label. So that is a convention actually. And this is kind of more meaningful when you have imbalanced class distribution. Like in fraud detection, if you're doing, if you say credit card fraud, right? Let's make it more credit card data is available to you, and I'm asking, okay, fine, build a classifier that will detect whether the transaction is fraud or not, right? So here you would expect the class distribution to be biased or unbalanced, I should say, not biased, unbalanced. So in case of unbalanced data, right, very often the data size which is smaller happens to be the positive class, right? Like spam. If I give you the emails, then we should expect that less number of emails will be spam. But yeah, that would be the case. And similarly for the fraud also, if I give you the credit card transactions, then the number of fraudulent transactions are going to be smaller compared to the genuine transactions. But if the data is given to you which is 50-50, like the height and weight of a population, so here we can assume that 50% I'll have female population, 50% I'll have the male population. So wherever the balance is even, there we can probably ignore for them. For that case, I can either pick female as the positive or male as the positive. It does not matter that much. But where you have imbalance and you want to predict the label which corresponds to a lower count, then we pick that as the positive, right? And once you understand positive and negative, then the next thing is simple. the positive label gets the number 1. Okay, and the label, the negative sample gets the value 0, right? So that's how we will have to relabel the data. Okay, question. All right, so this is what we had done in the last class as well, and we thought, okay, fine, now our target is numerical, right? The target that we need to predict is 1 or 0, and we know that linear regression is something which can predict a number for us, right? So we thought, okay, fine, why not apply linear regression directly to this data once we have changed our labels to 1 and 0, right? And then we realized that the way a linear regression model fits the data is not what we are looking for, because linear regression tries to pass through the middle of the data, right? Because it would try to minimize the residue. What we are looking in the classification is to find out the decision boundary, right? Something like that we have already gone through. We are looking for decision boundary, a boundary such that once we have it and a test data is given to us, we will decide by looking at this boundary that whether, you know, this test data happens to be in this, say, positive class, or whether it happens to be in the negative class, right? So our interest is in learning a model that will provide us decision boundaries. Okay, decision boundary could be linear, could be non-linear. So this is linear, straight line, right? That will happen when you are using the features that, well, we will be applying the linear regression. What may happen is, let me phrase it this way, it all depends on our data, like how is the data distributed. If we can see that there is a possibility of having a linear classifier, which means finding a line which could divide this data into positive and negative class, then that's fine, right? But it may happen that the decision boundary that we have may not be linear, right? Like quadratic, like, you know. So in that case, just like the way we had done in linear regression, we'll have to think about including other features as well, the square of the original features or the multiplication of the original features, right? So all these things we did, right? And then we figured out that, you know what, since we have to somehow come up with a decision boundary, so it will be good if we could start thinking in terms of probabilities, right? Something that we could borrow from Nat Silver's philosophy, that let's build a model which would come up with the decision boundary, but then this decision boundary would be based on the probability, right? So what it would do, it would learn the probability of the positive class, right? Probability of x being 1, right? So that's what we have to learn. That's what we have to learn in the training process, right? So for that, whenever we need a probability, we know that the probability value falls in the range from 0 to 1, our ideal choice was logistic function, right? And we have used logistic function in modeling. We learned about it, logistic function at least. So the logistic function will help us. So what we have to now do is that whatever we've learned in linear regression, we need to just use that in combination with logistic function and build a model. All right, and we know about logistic function, which is sigmoid function, the same thing. And you know, its value at 0 is half, 0.5, right? And f of infinity is 1, f of minus infinity is 0. So all these things are helping us, okay? And the linear regression along with this logistic function resulted in our logistic regression model. All right, and what we had to do in our logistic regression, like how are we predicting the label? So what is x? X is a data for which we need to find out its level, right? And which form we are predicting the level? We are ultimately finding out the probability of this x being 1. 1 means the probability that this input data x that you have given us belongs to the positive class, And that's what we are learning. That is what our classifier will give us. The logistic regression will give us the probability of the data or X being being in the positive class. So that's the reason it is important for us to have the notion of what is positive and what is negative. So here we have done all these things, right? Just for the sake of continuation, I'm covering these things one more time. So this expression that you have is coming straight away from the linear regression. Okay, so what do we learn in linear regression? We would learn these weights, all right, and we would find out the best weights or the optimal weights which would reduce our residue in linear regression. But now, since the same thing we have to use, the same concept we have to use in logistic regression, so we will take this term from here, right, and we'll put that right here in the exponential term of the sigmoid function. All right, and that's what logistic regression is in terms of formulation. All right, and yeah, if you implement it in this way, and ultimately, we need to think about the cost function as well, and that's where I think I stopped in the last class. We will look into the cost function, but before the cost function, this is how we will be generating our output, okay, which is a probability. So if you understand what this fx is, then we can go ahead and think about the cost function, which we will have to optimize using the gradient descent. Now, assuming that each of our n training example are labeled as being in either class 0 or 1, now we seek to identify the coefficients W that will give the high probability on the positive class 1 items and low probability on 0 items, right? So this is something we need to keep in mind, and we need a cost function, right? And the cost function we need a cost function to value a probability P for an item of the class C. All right, so I think the same, these are the points which I was trying to explain in my way. Let's move on to the cost function, right? Because that, I believe, is probably the most important and difficult thing to understand for logistic regression. We may have a difficult time. Okay, so we followed all these things, and this will help us in formulating our cost function. So what do we want? Let's try to read it and I'll explain. We want 0 error when for the best probability. What is the best probability? I'll tell you. And this error should increase, and this error or the increasing cost, the cost should increase as the class prediction gets more and more wrong. Let's try to understand it. We are saying that, whenever we knew that, the person X1 is positive, right? We knew that X1 is positive, and the corresponding target value is 1, and we are feeding that in our logistic regression. Then we want this fx to be close to 1, right? So if it is on the expected lines, then the cost should be close to 0, right? Very intuitive. But if it was other way around, X1 was 1, but my X1, which is being f of X1, which my logistic regression is returning, is 0. Then here we need to penalize, right? So that is the intuition behind it. So our cost should have this kind of feature in it, okay? So that is when my y is 1. Y means the true level is 1, right? So for the positive case, this is what I'll do. For the positive case means when y is 1 and my logistic regression is returning 1, then I am happy. I won't give any cost. I won't give any penalty for that. And it may not be 1, so there should be some function which could scale between 1 and probably infinity. Infinity, when it is doing horrible, I will penalize it heavily. Okay, so when we are thinking about positive, similarly we need to think about negative case also. Assume that X2 is a negative sample. That means this is a healthy person, but my logistic regression is labeling that as a healthy guy, right? So I should have a cost which should be high, maybe, close to infinity, pretty high. Whereas if I know that, this guy is healthy and my logistic regression is also calling that healthy, so I don't need to give any cost, right? So the cost should be 0. So this is the only thing we need to understand. If it's 1, you're returning 1, no cost. If it is 1 and you're returning something close to 0 or 0, I will penalize this classification, right? Same thing I have to do with the label being 0 also. If it was 0, you're saying 0, no cost. If it was 0 and you're saying close to 1, I will penalize. Is that thing clear? So one thing interesting that we have in case of logistic regression is that here the cost function that we have is in fact the combination of these two, right? You can see one curve which is blue in color. There's another curve which is red in color, right? So in fact, these two curves that you have are the cost functions. The blue is for the one where our original data is positive, right? So when the original data is positive, we will determine like, oh, how should we penalize? So let's pay attention to this guy here. This is in fact minus log of f of x. Let me put that f of x just to keep it simple. All right. So why did we pick this thing to be minus log of f of x? It's extremely simple to understand, right? See, y is 1. This is only for y being 1, right? For y being 0, we have a different function. So if y is 1, then we want the result of fx to be close to 1. All right, or in ideal case, it should be 1. If that is the case, then think about this value, minus log of 1, which is 0, cost being 0. Perfect, that is what we want, right? And if the value is very close, if fx is close to 1, right? If fx is tending to 1, then, this value could also tend to 1, or minus of something, very small. So that means we don't want to penalize it that heavily. Why? Because, the actual label is 1 and logistic regression is also kind of giving a value which is close.
Professor, don't you mean like it would be positive 0.001?
Oh, it should be positive. Yeah, it should be a
Because
positive.
like log is always negative in
Yeah.
the range of 0 to 1.
Thanks for helping me out, right? Yeah, thank you so much. Yeah, it should be positive, right? Yeah, we need to think, and that's the reason we have the negative sign here. That's the reason we have negative sign here, right? So the biggest value that we can have would be a 0. I mean the log of thing, right? Fx is a probability. Thanks for helping me out, man. Fx is the probability, and the maximum the probability can take a value is 1. So the maximum value the cost will take is a 0, right? And that's the reason we have a minus here. It will be minus. So the cost would be a positive value. Thank you so much. All right, so you can see here, right? So what is it? H theta, which is fx. When h theta is 1, that's what we want. So the cost is 0. But as you are moving away from 1, see the cost going higher and higher. All right. So if you predicted some value very close to 0, look at the cost, how heavily we are penalizing. And it will go on, right? It's not meeting, I think it might meet in the infinity. Fine. If you understood this case for y is equal to 1, then understanding the case for y is equal to 0 is not difficult at all. This is similar to this one, very close to this one, right? And what is that? Minus log of 1 minus fx. I'm changing, h theta to fx because that's what we have here, right? That's what we have here. Which means what our logistic regression is returning. All right, so let's try to understand. If y0 was 0 and my regression is returning 0, logistic regression is returning 0, then this will be minus log of 1, 0 again, ideal situation, no penalization, right? Otherwise, in the other extreme, if, the reality was a 0, but you returned a 1, then minus log of 0. And log of 0 is minus infinity. Minus infinity and minus, this is infinity kind of a thing, right? So if you reason that way, then this is simpler to follow. How did these people arrive at this expression? Well, for that we will have to probably read their research paper. Okay, so is it making sense now? This blue curve corresponds to the cost that we will associate for the positive label. The red curve corresponds to the cost that we will associate with the negative original label, right? Like what is your classifier doing? And interestingly, well, this is not the final cost function. The final cost function is in the next slide. Are we good? Questions on this? Okay. All right, so this just explains whatever I was telling you, that log of 1 is 0. Great. Okay, and log of 0 is minus infinity, right? Just work on it. It should not be difficult for you to figure out that log of 0 is minus infinity. And the cost that we have here, this will help. We need to understand this formulation. The cost that we have is defined this way, which means that when we know that the true label, this is the true label, right? When we know that xi has the label 1, then how do we test its cost? Then we will use this expression, which is minus log of f of xi. All right. And for negative instances, this is for positive instance, right? For negative instances, say 0. 0 means when we know that this xi now belongs to the zeroth class, negative class, and we are checking how well our logistic regression is doing on that, then for that we will use this function, which is minus log of 1 minus f of xi. Okay, questions? Now the most I would say beautiful, right? I like this concept, so I would say beautiful. The most beautiful thing is like how these two things have been combined into one expression, which is this one right here. Okay, so what do we need? We need the cost for the whole training data, right? So we are looking for the cost for each data sample, whether it is positive or negative. I want to find the cost, and ultimately I will average that out, similar to the way we have done for linear regression. We'll average it out 1 by n of the cost associated with the logistic regression. F is what logistic regression is doing. The result of logistic regression, which is returning a probability for xi, right, with some original level is right here, right? This is the label. Now we are adding more detail here. Okay, we are not saying just f of xi. We are also saying f of xi along with w, because w is what we have to learn in the optimization process. Is that thing clear? Look at j. J is the function of w. All right, so w is what we are learning. X is just the value that we have. We can't change anything in x, but yes, we are looking for the best w's. All right, so this is more general. We want the cost associated with every data sample xi. There are n such data samples, and the cost would be would be a function of the label. Like what label is it? Is it positive label or the negative label? And we have just seen that there's one expression for positive label and there's another expression for the negative label. And we need to intelligently combine these two into one expression. So how do we do that, right? So 1 by n, the same 1 by n, where from this negative is coming? These two signs, right? For both the expressions we have negative, so let's take the negative out. So that's the negative that we are getting from the previous two expressions. So we are combining the case where our training data belongs to be positive label and the case where it belongs to the negative label. That's what we have here. This is for positive label and this guy is for the negative label, right? These are the two things anyway we had to add. But what is this guy doing here? Yi and 1 minus yi. This is the most interesting aspect that we have in this whole expression. So let's try to understand like what is the impact of multiplying by yi in this cost, which is associated with the positive label cost, and 1 minus yi for the cost which is associated with the negative class. All right. So see, whenever you are dealing with the positive level, then their yi would be 1. All right. So for the positive, when your data sample is positive, then only this term will be effective. Why? Because yi is 1. 1 multiplied by log of fxi w. And what will happen to this term? This term will cancel out. Why? Because yi is 1. So 1 minus 1 is 0. So this term won't count. Okay, good. And what will happen when your yi is equal to 0? Well, in that case, first term would be a 0 because you're multiplying 0 by this first term. Whereas 1 minus 0 is 1. So, the second cost will be effective, right? That's it. That's simple. Question on this? You need to reason, right? Or probably it's just too intuitive. I think it's not so intuitive, but anyway, if you understand, great. If not, just let me know. Are we good to move to the next slide? And interestingly, this whole expression that you have, I was looking for its plot. I could not find the plot, right? The reason why I was looking for a plot was to just understand that. Is it looking like convex? Well, I failed, but the reality is it is in fact a convex function. This whole j that you're looking at is convex, right? And if the function is convex, then yeah, you can apply the gradient descent optimization approach for that. Question? All right, then let's move on. So the loss function here is convex. That is the great news. And we can find the parameters by the gradient descent, right? So yeah, you can either use batch gradient descent, which means you would consider all the training data in order to find out the optimal value for W, or else you can use just the stochastic gradient descent. Stochastic gradient descent would be more efficient. You'll converge to the optimal faster than the batch gradient descent. Questions? All right, so we have some result, right? So we have some result, and I thought, okay, I should discuss that. At least we should go over that once. So here is some result that was obtained when the logistic regression was tried on the classification of people into classes like female versus male on the basis of their height and weight only, right? So you can see here, this is the the result graphically. And if you're interested more in numbers, then you should see that in the red region. Red region means the one. Wait a second. Oh, okay, fine. So in the red region is for women, right? In the red region, we had 229 women and 63 men, right? So 229 true women, we should say, true positive, we cannot say here, but yeah. If you're considering women as a positive, then yes, we will say 229 as true positive, right? That way we can interpret. But if you want to keep it very simple, then we incorrectly classified 63 men as women using this logistic regression, right? And correctly classified 229 women as women, 223 men as men, and incorrectly classified 65 women as men. All right. So although we have this issue mentioned in context of logistic regression classification, but this is a global problem, right? Global, when I'm saying that, then it means that this problem we have even in ANN, artificial neural networks, right? So if the data is imbalanced, then that's a problem for any classifier, right? We need to fix that. And if our data, if our model is not multi-class, if my model is binary classifier, then how should I extend that to multi-class classification, right? So these two issues that we have, which we are discussing from logistic regression point of view, are in fact general issues which we want to address in any classification model because of the imbalanced class distribution. So consider a scenario where we have one positive example versus 1 million, I think, right? If I'm not wrong. Negative example. So what will happen to the logistic regression? What will it try to do? Well, ideally, we would like to have, assume that this is one sample and these are 1 million samples. Ideally, we want this, logistic regression to come up with a boundary, decision boundary, which should lie in between these two samples, right? Positive versus negative. But what will happen is that the logistic regression will try to be very far from the big cluster, right? It will be very close to here, right? So it won't be finding the perfect classifier, the decision boundary, because of its nature. All right. So this is a problem we will have in all the classifiers. Okay. So we won't have a very good classifier as long as our data is imbalanced in terms of the number of classes. Well, you know what? Discussing these things from a data science point of view is kind of not so important these days, because for these libraries that you use, there's only one parameter which you can use, and the library will take care of balancing the data. So conceptually you should know it, but addressing it is extremely easy when you're modeling, right? Extremely easy, just to one parameter which you need to pick. Okay, so good news is that these libraries are built in with the capabilities that they will do it for you, right? You should know the theory, but anyway, they will do it for you. If you have to balance the data, then the library will balance the data for you. But how to do it, that's something we need to know theoretically. Okay, so we need to have equal number of positive and negative examples ideally, but that's not always possible. So we need to look into the ways, like how should we balance. Okay, so what is the approach that people are following? How are these libraries implementing this balancing act? So first, the simplest approach would be to, let's work a little harder. Let's reach out to a lot of people, maybe search for it online, and somehow try really hard to find the more members from minority class, right? We would try. If we find it, great, right? Then we won't have to think of any artificial means of balancing the data. Okay, let's try it hard and find the more samples from the minority class. Fairly simple. The other approach is also simple, but that is applicable when we have a lot of data, right? So assume that, I have millions of negative records, millions of positive records, and billions of, negative data. So what I'll do, well, from this negative data that I have, I will only consider millions of records, right? So that I have million positive, million negative. So that liberty of discarding the class, the minor, this liberty of discarding elements from the majority class will only have when we have significant, data set from the minority class. Then we can throw some data from the majority class. But if the scene is that the majority class data is also not much, then probably this is not advisable. We would like to keep the whole data, because every data point or every data sample has some information, right? So discarding is not always encouraged. We should not discard the data, even if that is from the majority class, right? We want to try the other way around. So what is the other way around? This I'll cover later, because this is little intense. Replication, right? What is replication? Well, replication is very simple term, but statistically we call that oversample. What does this oversampling means? Assume that, a very simple scenario, the majority had 100 data points, right? And minority class had 50. So what I would do, from these 50 samples which I have from the minority class, I will randomly sample 50 more points, right? And I'll make this whole data as 100. Now you argue, and this is very obvious, that even by doing the random sampling, I'll end up with the data points which will be multiple, right? eventually I'm replicating the data. So the question is, are we gaining anything by doing it? The answer to that is yes, we are better off. Okay, it doesn't matter even if you are oversampling, right? So oversampling means from the minority class, we will um, use some sampling technique and we will oversample. We'll make sure that eventually we have 100 data samples so that our data is now balanced. 100 majority class samples and 100 minority class samples. Okay, so oversampling and undersampling. Whenever we talk about oversampling, we also discuss undersampling. So oversampling is something which we apply on minority class, right? But if a minority class has a decent size, say in millions, and I have billions of majority class, then what I will do, I will undersample from the majority class, and from these billion records, I'll only sample some million records, right? So undersampling we perform on the majority class, right? And oversampling we perform on the minority class. Anything to explain? Good. If not, then let's go on to this one, which I believe is probably the best, right? And as a little difficult to understand, but anyhow, let me try that. What you can do is that, don't oversample, don't undersample, right? What we can do is we can tweak the cost function, right? And how should we tweak the cost function? We should apply some weight, right? And where should we apply the weight? Let's go back to the cost function. Right. Here we have that. All right. So here you can see that we don't have any weight at all, right? And if I know that, the positive class is less compared to the negative class, then I will incorporate some weight, right? So WP multiplied by this whole thing. WP means the weight associated with the positive label. And similarly, I'll say W and multiply it with this term. So what we are doing here is that we are tweaking our cost function in such a way that if the classifier is making any error in classifying the label which is in minority, then we will penalize that act heavily compared to the misclassification which our classifier is doing for the minority class. Does that help? Right? And then for weight, we need to make sure that WP plus WN is equal to 1. The rule for the weight is same, right? The weights adds up to 1. Questions? Yeah, you should know these techniques, okay? How do we balance the classes? Now, the most interesting thing which I found here was SMOT, synthetic minority oversampling technique, right? So what it does is, in fact, you would sample, right? Say you from this minority class, what you will do, you may sample some data points, right? Let's say we sample 5 out of, randomly we'll get 5 samples. I'm just coming up with an example, right? We'll sample some subset of these samples, and from these samples that you have obtained, you would generate a synthetic training data, right? So this is synthetic. This is not the one which was originally there. And how do you synthesize? Now you can, use some intelligence. You can either average all the features, all right, or you can find the median value for all the features from these 5 samples, and you create a new sample, right? So yeah, I like this approach, synthetic minority oversampling technique. Simple, but we are adding a new sample to our data, which is kind of, synthesized on the basis of the actual real samples that we had in the data. Questions? And there's well, it's not exactly smart, but what our textbook mentions is that when you're replicating the members from this smaller class, then you can also introduce some random perturbation. So what does that random perturbation means is that, For any feature that you have from when you are replicating, right? So a replication without perturbation would be having multiple copies of a data sample. Now, when you say that let's have replication with perturbation, then that means you'll be adding some very small noise to the features, little bit. It should not be made an outlier, just changing a little bit here and there, right? So that we get a new data point. All right, good. Let's move on then. Now to the multi-class classification. So what is this multi-class classification? Well, we did see this binary, just two classes. And here, the multi-class that we are looking at is simple too, because we have just three classes. But yeah, it's looks simple, but it's not that simple. Because what we have done till now is that, we gave some numbers. If this is my positive, I'll put 1 for this guy. If this is negative, I'll put a 0 for that one. And then we'll do the training, and we can apply a binary classification technique like logistic regression. So since we have done something like this, we will be tempted to do something like this also, 0, 1, and 2, right? But this is bad. We should not do it. As long as it was 0 and 1, it was easier for us, right? Because we could apply logistic regression with the cost function that we have seen. Now, what we can do is we can apply softmax. This is something I need to I'll cover that in the next lecture. Softmax. There's a softmax cost function, right? If you apply softmax cost function, then you can extend that to the multi-class classification using logistic regression. Okay, but here extending that like this is not going to work, right? Why? Because when you have 0, 1, and 2, then there is a side effect. This label gives us an idea that probably 2 is greater than 1 is greater than 0, which is bad. All right, so we need to avoid that. So that's what we are saying here. It is natural to represent multiple classes by distinct numbers. Like, as an example, if you have some data that is about the color of the hair which you want to predict, and there are different classes like people with blonde hair being 0, you're putting this number, brown hair being 1, red as 2. Okay, so this is not a good idea because these things will have some ordinal sense, ordinal data, ordinal sense, right? So this will work in the case where you are trying to predict the rating. Okay, assume that I give you a project where you are given movie data, all right, and I'm saying, okay, fine, let's predict the rating of the movie. So there you will have these values like 4-star, 3-star, 2-star, and 1-star. So for these stars, you can use these values like 4, 3, 2, and 1. So here, the rating being 4 has some ordinal sense in that. Like 4 is greater than 3, 3 is greater than 2, 2 is greater than 1, right? So if we don't have any ordinal sense in the data, right, if there's no ordering associated in the label, then we should avoid doing something like this. Okay, now the question is, okay, fine, but what should we do? Well, we will use this approach, one versus all classifiers. So what is it? Let's try to understand. Extremely simple, but very common. People use it a lot. So when you have these three classes, right, and you want to use binary class for doing this three-class classification, then what we can do is that we can divide this task into multiple stages. So what does it mean? For these three classes that we need to consider in classification, what we will do, we will come up with the three binary classifiers, right? So what the first classifier will do, first classifier would try to come up with this boundary. What this boundary will do, this boundary will separate, the triangle objects from the remaining. Okay, so it is one versus all. One versus all means we have two classes here. Class 1, which represents the objects with the triangle shape, and the class 2 here represents those objects which are not triangle. 1 versus all. Okay, so my first classifier will identify triangle objects from the other shape objects. Same thing I can do, and I'll come up with another classifier. This is the second classifier, okay, which will separate. When I'm saying classifier, that means binary classifier. First binary classifier is separating triangle objects from the circle and cross-shaped objects. The second binary classifier here that you can see here, is the one which is separating your circle objects from the remaining shape. All right, and then you have the third classifier right here, the third binary classifier, which will come up with a decision boundary that separates the red cross objects from the remaining shaped objects, right? So what you would do, if a data is given to you, once you learn all these three classifiers, right? You have classifier C1, you have classifier C2, these are all binary. You have classifier C3. C1 is for triangle, C2 is for circle. My triangle looks like a circle. Let me make it look like a triangle. And then C3 is for cross. Now you got a different shape. Oh, what should be that shape? All right, we got a rectangle. And we don't know, like, to which class rectangle should belong. So what we do? Well, let's check with every classifier, C1, C2, and C3. They will have some values, right? Now, whichever classifier is giving me a higher value, I will classify it in that category. Does that help? Right? Yeah, so we can build multi-class classifier by using multiple independent binary classifiers and select the class of highest probability as the predicted label. Okay, so that was it on the logistic regression. Right?
I have a question.
Sure, go ahead.
So what happens if all three classifiers guess that it belongs to the other class? So what if the triangle classifier says outputs a low probability for triangles, the circle one guesses a low probability for circles, and the cross one does the same thing? What do you do in that case?
See, wait a second, right? Let's think about values, right? When you're saying we should have some values, right? What will happen? So do you have some values in mind so that our discussion is
maybe each of them guesses that it's only a 20% chance that it belongs to their own class?
Okay, so you're saying when we have a tie, then what to do?
Not necessarily a tie.
I think you meant like if it was like 0.2, 0.3, and 0.4 or something, they'd all be under 50. So
yeah, if
it is the binary classification, like piecewise, each of these would basically say no.
Yeah, so what I would do is I'll consider that in this category, because whichever probability is higher, we would decide in that favor, right? So there'll be these things like confidence. What is our confidence in classifying it as class X and not versus 0 and the circle and the triangle? Well, that would depend on our probability. So our probability is okay, you can quantize that, right? But as long as you have a higher value, then you would classify it to that category. We would worry if it is all the same, 0.33, 0.33, 0.33. But another interesting thing is that these values may not add to 1. Do you get that? Although these are the probabilities, but these probabilities may not add to 1. It may be a little more than 1 as well. Okay. Yeah. So rather than making it complex, I would say, right, I would answer the question that the student asked on this basis, that whichever probability is higher, you assign it to that class. Select the class of highest probability as the predicted label. Okay. Good. Now let's move on to a different classifier, which is our nearest neighbor, and I call it cutest, right? Cutest because it's very intuitive, very simple to interpret, and very much practical as well. Well, it gets a little efficient. That's the problem with every cute thing. All right. So, what do we have to do in the nearest neighbor classification from the training data, right? So let me take you to the example and tell you like how the nearest neighbor classifier works, and then we'll worry about the remaining details. Anyway, we'll discuss that. So this is your nearest neighbor classifier. All right, how does it work? It's very simple actually, right? That's the reason I thought I'm calling it the Q test one. We have the data, right? So you can see that the data is represented by filled circles of two colors. One is red and the other one is blue. And we are considering the red circles as positive class and the the blue ones as the negative. Okay. And then these question marks are the few points, right? So this is one point, this is another point. I need to decide like in which class should I classify it, right? So in this KNN that we have, K stands for a value, right? So this is up to us, like what value we want to assign to it. And then N is for nearest neighbor. So this example that you're looking at is for five nearest neighbor, right? Here we will consider five neighbors and then we will decide that which class this test data belongs to. Okay, so look at this point. Let's start with this first point and then we'll think about the second point. So you're given the training data, right? And interestingly, there's no training at all, right? Let me see. Yeah, there's no training at all. Okay, so you may argue, keep thinking about my statement, I might be wrong. So whenever a test data is given to us, we will try to find out its nearest neighbors, five nearest neighbors. So look at it, right? One, this is nearest, then maybe this guy, and then this guy, or this guy, right? So these 5 points that you're looking at are the nearest neighbor of the point 1. All right, so we will first find out our k nearest neighbors, and then we will look at the majority label. Okay, so I am not saying what is the label of my nearest neighbor. I am saying what is the majority of the label in my 5 neighbors. Okay, so which is not difficult to figure out, right? So for this point, out of these 5 nearest neighbors, 4 data points, they belong to the positive sample. Okay, so I will classify this as positive. Okay, and how about this guy here? Again, we need to find out 5 neighbors, 5 nearest neighbors, 1, 2, 3, 4, and 5. Now look at their labels, right? So we are kind of having a voting. So when you look at the voting, then interestingly, it is close. I mean, it is a tight voting here compared to this one, right? Here it was 4:1 in favor of positive. But in this case, it is 3:2 in favor of positive, right? So even then you classify this as positive, right? So that is the reason I consider KNN as the, very intuitive, simple, and cute classifier. What you need to do is you need to have a value of K, right? And what would be an ideal value of K that you need to pick in the evaluation stage. Right? So if you remember, I told you that when a data set is given to you, you need to split the data into training, training, evaluation, and then testing. So testing data is the one that you should not be touching at all, right? You should touch testing only when you have to finally evaluate your performance. Training you'll keep, right? We are not doing any training, but in a way we are picking the nearest neighbor from the training data only. All right, and then the evaluation data you can use to check like what value of K is working best for you. All right, is K is equal to 1 working best for you? If K is equal to 1, then this data point should be classified as, are you following me? When K is 1, then what class should I label this point as? Point 1 goes to which class, positive or negative?
Positive.
Sure.
The red class, right? Wait, where's the dot? Oh, wait. Oh, we're talking about the other dot.
Dot is right here actually.
I was looking at dot number 2.
Yeah, sorry. It will go to this class, right? Negative, because that guy is the nearest. 1 means the first person who is nearest to me. My neighborhood is just 1. Okay. Only when you are having more, then you need to think about it, right? So when it is when it is nearest neighbor, then that means you don't need to consider k. K is equal to more than 1. You just need to consider the person who's closest to you, just one person. So in that case, this guy is closest to blue, which will classify it as negative. For this point, I think the positive. Well, it is a close tie, right? We need some value, but I don't know, one of these two, whichever is closest. So I think I should stop right here.